Hello everyone, my name is Christina and I'll present our work, Limix Limiting Lamport Exposure to Distant Failures in Globally Managed Distributed Systems. This is joint work with Georgia, Jay, Michael, Jose, Gaylor, Kilong, Pierluca, Vero, and my PhD advisor, Professor Brian Ford. Let's look at an ideal situation. Here we have Alice and Bob, and they collaborate on a document. For example, this could be in a cloud environment. Alice might think that the updates to this document take the shortest network path. And as a result, no failures that are outside this path would affect Alice and Bob. So somehow there is this illusion that there is a bubble that protects them from these remote failures and slowdowns. But their intuition is wrong, because with most of today's systems, failures anywhere in the world might actually interfere with their interaction. So our goal is resilient access. We want to get as close as we can to this ideal. We've seen the ideal situation, but now let's see what reality really looks like. Here we have the same figure as before. We mark the interaction distance between Alice and Bob with some metric, and we also mark the distance to failure. We want to know how likely it is that a failure at a particular distance can affect Alice's and Bob's interaction. I'll show you what happens in today's systems. So on the x-axis, you have the interaction distance, and on the y-axis, the distance to failure, and the dotted line represents the connectivity. In the upper part of this graph, you will see the effect of remote failures on interactions. And what you see here is that even very localized interactions between 0 and 50 milliseconds, for example, are affected by remote failures. And the same holds true even for interactions that are a bit far away. On the right, you see the results of our system, and we provide significantly better availability guarantees. This is what I'm going to present you today. But why is it that faraway failures affect local interactions? So in reality, there isn't just one shared document, there are multiple replicas, and replication masks individual failures. In this illustration, the system can withstand two failures. But replication adds a dependency on a quorum. Now, Alice needs to be able to reach a quorum of replicas for strong consistency. And this is what complicates our system. I mentioned individual failures, but what about partitions? One challenge is that we want the local resilience guarantees, but we are in a globalized system. And the CAP theorem tells us that under partitions, we need to choose either strong consistency or availability. But many systems make the simplification that partitions are rare events. And because they are unlikely to happen in practice, we shouldn't worry about them. And most of the time, we should get both strong consistency and availability. But this simplification is rather naive. We can't really say that all partitions are rare events. And this is because besides individual replica failures and full-blown partitions, we have a whole range of failures in between. And these are called gray failures. They might start small, like a network element or a replica failing, but then they cascade into more failures. And being resilient means we need to be able to withstand all these different types of failures. To achieve our goal, we'll look at the Lamport exposure of the interaction between Alice and Bob. We define Lamport exposure in our hotnets paper. Exposure is a user-centric concept. Alice cares about her access succeeding. For example, when Alice wants to fetch Bob's updates, Alice's Lamport exposure is given by the set of all distributed system components. This could be servers, routers, and so on, and the software dependencies, which, for example, could be replicas, whose failure could contribute to slowing or stopping her activity. And what we want is to minimize this exposure. So we saw that remote failures can affect local interactions, but how many local interactions are there actually? Is this relevant? To approximate the access distribution of applications, we use the top 100 websites in 5 countries. In the figure below, you see the percentage of traffic to these websites that comes from other countries. And what we see here is that we have a dual access pattern. There are many local requests, but also many requests from outside the country. And we conclude that applications must support efficient global access while prioritizing maximum availability and performance for local users. So is geo-replication going to come to our rescue? This is the roadmap of today's presentation. We already looked at the motivation. I'll continue by presenting the problem, which is the exposure of metadata. Then I'll present our design of an exposure limiting metadata service. I'll briefly explain auto-zoning, which is our way of systematically limiting exposure. And finally, we'll go through the evaluation. So with geo-replication, data might be localized, but metadata might not be. In a local infrastructure, such as a private cloud, local clients know that all objects are local within this private cloud. And so there can be remote failures, but they can only affect remote clients from accessing the data. But with a globalized infrastructure, objects can move anywhere. And even when the object is local, the client doesn't know it, and it needs to look for it. And a lookup is going to add this another layer of indirection. The client now needs to go through a global coordinator outside the area where the object is actually localized. And because this global coordinator is exposed to failures anywhere, lookup may fail for both the local and the remote client. But this shouldn't surprise us because, as David Wheeler said, all problems in computer science can be solved by another level of indirection. That's except for the problem of too many layers of indirection. Now let's see why geo-replication is not enough. There are two documents geo-replicated in the area where they're accessed most. The challenge is to be able to locate these documents without leaving the area. But the user here is unlucky. The document he's looking for is in the same area as the user, but his query needs to go outside the area to the discovery service. So he is exposed to failures outside. And no matter where we place this discovery service, there will always be some users in some areas that are unlucky. So the intuition for Limix is that the exposure of data access depends on the metadata, which is the discovery service. Thus, metadata needs to share the data's fate, or the data's exposure. Limix is a control plane that limits exposure of metadata. And Limix control plane will support existing strongly consistent key value data planes wherever the data might be located with item migration. Let's look at how we limit exposure of metadata. So instead of having one discovery service, we can replicate it in all areas. So let's just have n discovery services, like in the figure. So now the user just needs to query the local discovery service to find any document, both document 1 inside and document 2 outside. But you've probably guessed it, now the issue is that each discovery service is going to store pointers to all documents, and this is going to be a lot of overhead when a document migrates to update all these discovery services. And note we would need to do the update without knowing if actually users are going to be interested in a certain document, right? So that's quite a bit of overhead. So the next strawman fixes this problem. So we'll have local discovery services storing pointers only to local documents. This is crucial. But then we'll also have a global discovery service storing pointers to all documents. Lookup works now like this. First, the user is going to query the local discovery service. If it doesn't find the document, it means that the document is outside. So then it's going to query the global discovery service. So the advantage now is that the zone serves load only for documents living in that zone. So now the remaining goal is to support finer grained zones. We can simply do that by adding as many zones as we want in a sort of pay-as-you-go model. The trick is that each zone is going to store pointers just to zone documents. I was saying that the data plane is strongly consistent, but when an item migrates, it is pretty challenging to find the latest version of that item. And there are several challenges here. First, note that the discovery service in each zone is strongly consistent, but the metadata updates in different discovery services are not atomic, and therefore metadata as a whole is inconsistent during item migration. Because metadata alone can't give us the latest version, Limix needs to track the latest version of the data. And finally, we will need to limit exposure while the document migrates. Check out our paper for details on how we solve these challenges. Now I'll briefly present auto-zoning. Our auto-zoning intuition is that we want to support dynamic local and global interactions. This means that any client accessing any item is guaranteed to have a limited exposure upper bounded by a small delta around them. Without going into details, take a look at the figure on the right. Client accessing item 1 has exposure 1, which is smaller than the client accessing item 2. But the client will always find an area that fits this delta. Auto-zoning sounds great, but what is the overhead? Take a look at the figure on the right. Here, each site is part of multiple zones. We know that the number of zones is logarithmic in the number of sites by construction. But the question is, how many zones does a site expect to run? The figure shows on the x-axis the number of zones and on the y-axis the load. As the system grows, each site expects a logarithmic increase in the load it needs to handle. So how well does all of this work? Administrative zoning is a simple but common scenario. Here the object is administratively localized in a single region. We know that Limix has the best of both worlds compared to classic geo-replication and a private cloud. It has both global manageability and resilience to remote failures. But this doesn't come for free. There is a cost per region deployed. So we take the case of 2 nodes in each of the 3 deployments. There are, of course, many more nodes running the system, but we want to understand the cost per node. I'm going to show you the data for bandwidth, but we have similar data for CPU and memory. So private cloud has the lowest bandwidth. That's because there's less coordination between nodes. In geo-replication, all the nodes participate in a single deployment and see similar costs. There is no distinction between inside the jurisdiction and outside the jurisdiction. In Limix, nodes inside the jurisdiction participate in 2 zones. So they have cost associated with these 2 zones. And moreover, there is some workload duplication. A node outside the administrative zone just runs the global deployment and therefore sees a similar cost to geo-replication. We conclude that this mode is suitable for a pay-as-you-go deployment, where every extra zone improves exposure but also brings costs. This is the more interesting scenario where we don't know where the users are and where the documents are. We want to be able to adapt. Therefore, we use Limix auto-zoning based on round-trip time, and we compare it with Physalia. Physalia is deployed as follows. There are several disjoint zones deployed as you see in the figure. And now we have a micro benchmark where we exhaustively look at user accesses. We take a test area of various radiuses, and then we take various pairs of users within that area. And then we disconnect this test area from the rest of the world at various distances. We want to see if, to locate the documents in the test area, users have dependencies farther than the disconnect boundaries. Our workload, representing the round-trip time between the user and the document, follows the distribution you see below. This is a realistic distribution. The results will use this plot. The x-axis represents the distance between interacting pairs, and the y-axis represents the distance to the failure. Users look up a document. We want them to be protected from remote failures. On the left, you have the results for Limix, and on the right for Physalia. First, we observe much fewer failures for Limix than Physalia. This is in part because Physalia offers no guarantees for user activity that crosses cell boundaries. We can also see the guarantee for Limix auto-zoning depicted by the stair dark line. Failures farther than the boundary are guaranteed to not affect users. We presented Limix, a global metadata service that protects local accesses from distant failures. Limix is suitable for strongly consistent data planes, has a pay-as-you-go administrative zone deployment, and an RTT-based auto-zoning that outperforms related work. Thank you. I'm happy to take questions.